Today we're going to move to section 11.4, which is geometric probability. And just a note, there are no classes on Monday or Tuesday. So the assignment I'm going to put up with a deadline of next Tuesday evening, and then I'll post the answers on Wednesday. So you have plenty of time and you can do it whenever works best for you. Before we talk about geometric probability, we need to review the definition of probability overall. Probability is the measure of the likelihood that an event will occur. If we want to find the probability of event A, which is written as the probability of A with whatever the event is inside the parentheses, you take the number of favorable outcomes and divide by the number of possible outcomes. You guys know that if you have a bag full of marbles and there's 7 marbles in the bag and 3 are red, then the probability of picking a red is the 3 favorable outcomes, the 3 red marbles, divided by the total 7 marbles in the bag. So it'd be 3/7. When you talk about probability, your answers can be anywhere on a scale from 0 to 1. And there's different ways we can write probability. We can write them as decimals. We can also write them as percents from 0% to 100%. A probability of 0 means the event is impossible. And as the probability goes up, 50% or 0.5, it is equally likely to occur or not to occur. And then when you get to 1 or 100%, it is absolutely certain that it will occur. I have 10 blue marbles. What's the probability that I pick a blue? 10 out of 10 is 100%. The problems we're going to do are geometric probability. This is a ratio that involves a geometric measure, either length or area. There's 2 principles that can be used to solve the geometric probability problems in this section. So, for example, suppose that point P of segment AB, so P is somewhere on this segment, is picked at random. If I want to find the probability that P lies on segment AC, the probability that it's between A and C, knowing that it is between A and B, is the length of segment AC divided by the length of segment AB. The second principle involves area. Suppose a point P of region S. So this is my egg diagram here. S is everything, the whole area. And I pick a point somewhere in S. The probability that that point P lies in R, my yolk, the yellow part, is the area of R divided by the area of S. The area of the region you want to be in divided by the total area that you know that it lies in. We can do all sorts of application problems using these principles. For example, it says, what is the probability of breaking a piece of 10-inch linguine into 2 parts and having one part be more than 8 inches? So my linguine is 10 inches long, goes from 0 to 10. We can think of that like a number line or like a length. And I want the probability of one part to be more than 8 inches. So if I want one part to be more than 8 inches, I need to cut close to the ends. I need to cut somewhere between 8 and 10 because that would make this other piece more than 8 inches, or cut between 0 and 2 because that would make this side more than 8 inches. When I figure out which of those regions are my positive outcomes, my probability is the length of the outcome I want, which is 4 out of the total length. 4 out of 10. I can write my answer either as a reduced fraction, I could write it as a decimal, or I could write it as a percentage. For a lot of problems in the homework, a fraction will make sense, or if they ask you to round, you can go to a percentage. Some of them will tell you which form to write it in. Here's another example where the length isn't a physical distance, but a time. The MARTA transit system trains in Atlanta arrive and depart the station every 15 minutes. This arrive, depart means one shows up and leaves right away. There's no wait time in between. Assuming you arrive at the Indian Creek station at a random time, what is the probability that you will have to wait more than 5 minutes for a train? So this is a repeating cycle that goes for a length of 15 minutes. We want the probability that you have to wait more than 5 minutes. The train is arriving here at the 15-minute mark. If you wait more than 5 minutes, you arrive sometime before the 10-minute mark. That's 10 out of the total 15, or 2/3, which is 66.7% approximately. Most people don't like to wait, therefore find the probability that you would wait less than 7 minutes. Well, here's 0 to 15 again. If I want to wait less than 7, I have to arrive after the 8-minute mark. So that is 7 out of the total 15 minutes. You would have to round if you change that to a percentage or a decimal. A dartboard is the perfect example for comparing areas with geometric probability. What is the probability of throwing a dart such that it hits within the red area, given that the dart always lands within the boundary of the outer circle? So we have to know that it's hitting the dartboard in order for this to work. The area, we would compare the area of the red circle to the area of the entire thing. The 5 here is this whole radius. The area of the red circle is pi times 1 squared. The area of the entire circle, everything, is pi times 5 squared. When we simplify this, the pi's are going to cancel out. I get 1 squared over 5 squared, or 1/25. In this diagram, I have 4 circles that are inscribed in the square as shown. Inscribed means they are just touching at the edges, and they're also tangent to each other here. What is the probability of an object falling in the circles, given that it falls inside the square? So we need to find the probability that it falls in the circles. So I need to find the area of the circles and divide it by the area of the square of the entire thing. Area of the square is 12 times 12, which is 144. The area of the circles is what I need to find out. I have 4 circles, and I need to figure out the radius of each circle. Because they are tangent to the edges and to each other, the radius is 1/4 of the way across the square, which is the length of 3. So I have 4 circles whose area is each pi times 3 squared. That's 9 times 4 is 36 pi with a denominator of 144. This can be reduced. 36 over 144 is 1/4. The answer is pi over 4, which is approximately 78.5%. What if there were 9 circles packed in the exact same square? Well, the denominator is still 12 squared, or 144. We need to figure out the area of the 9 circles. So it's 9 times pi r squared, where r is the radius of each of these circles. There are 6 radii that add together to make the length of 12, so each radius is 2. 9 times pi times 2 squared, that's 9 times 4 is 36 pi. We get the exact same answer of 78.5%. This is called the circle packing efficiency of a square. If you pack circles exactly edge to edge and edge to edge of the square, they will fill 78.5% of the square every time, no matter how many circles there are. Last examples. We want to find the probability that a randomly chosen point on the circle lies on the minor arc. So I know it lies on this circle. I want to find the probability that it is on the arc. The arc is this section of the circle. So we're going to compare the length of the arc. Arc length is the measure over 360 times 2 pi r. Notice the radius isn't given here. And I'm going to divide that by the length of the distance all the way around the circle, or the circumference. What happens? The circumference cancels out, and my probability that it is on the arc ends up being 171 over 360, which is about 47.5%. If that was a semicircle, you know the probability would be 1/2, which is 50%. This is a little less than that. Same circle, find the probability that a point chosen at random in the circle lies in the sector. The probability that the point is in the sector would be the area of the sector, which is 171 over 360 times pi r squared, divided by the area of the entire circle. And again, we see that the pi r squareds cancel out, and the probability is 171 over 360, or about 47.5%. I'm just going to show you this example quick. It says a ship is known to have sunk in the ocean in a square regions 100 miles on a side. A salvage vessel anchors at a random spot on the square. Divers search 1 mile in all directions from the point on the ocean floor directly below the vessel. What is the approximate probability that they locate the sunken vessel on the first try? We have to say approximate here because if they parked very close to the edge, the circle where they could search would be slightly smaller because part of it would be outside the square. So if you want the probability that the sunken vessel is somewhere within this circle, given that it's within the square, it's the area of the circle divided by the area of the square. And we get a very low percentage chance that it is found. This makes sense when they talk about searching for airplane wreckage or anything like that. The area, because it's ratio of areas, the percentages are extremely small because the size of the object you're looking for is extremely small compared to the region you know it lands in. So do 11-4 by Tuesday, and then I will see you next Wednesday.